Okay, we're on Unit 5, Activity 2, Wave Interference and Light, and I think the best way to tackle this one is to do a screen capture because there's some nuance in what you see. Now, the first thing that you have to understand is constructive and destructive interference. So from grade 11 physics, what you would have learned that if two crests meet or two troughs meet, they amplify each other. So if we have a crest that's 3 centimeters and it meets another crest that's 3 centimeters, they will be additive and it will be 6 centimeters. Now, destructive interference is when a crest meets a trough. And when a crest meets a trough, they will destroy each other. So if we have a 3 centimeter crest and a 3 centimeter trough, then they will annihilate each other. You will see terms in here like nodes and antinodes that you should know. Please go through that. Standing waves will not be important in what we're doing today. There is a simulation here showing some constructive and destructive interference. Make sure you go through that. Now, here's where we start to get where things start to get important. What you have to understand so far is what constructive and destructive interference is, and you have to understand what diffraction is. Diffraction is when a series of waves comes up to a small opening and it will make this pattern of crests and troughs as it goes through the small opening. Next step. Now we have a wave coming towards two openings. Let's talk about why this is important before we go any further. The pattern that's made of crests and troughs is going to allow us to measure the wavelength of the light. We need a pattern before we can measure something in physics. You must take the time to study the blue and red lines to figure out what's going on. Notice we have a dotted line meeting a solid line, a dotted line meeting a solid line, a dotted line meeting a solid line. Those will create nodal lines. There will be destructive interference. So the crests and troughs will cancel each other out. The red lines are called antinodal lines. Notice we got a trough meeting a trough, a crest meeting a crest, and this pattern could continue. It doesn't here, but troughs will constructively interfere with each other and crests will constructively interfere with each other. Know that a nodal line is destructive interference and an antinodal line is called constructive interference. Let me say that again to make sure I got that right. The nodal line is destructive interference, that's in blue, and the antinodal line is constructive interference. Now, what you may or may not see here is there's a number of ways to do the calculations. I'm going to focus on one way of doing it. So when I do the calculation, I'm going to focus on these nodal lines here. Blah, 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 blah. Let's go to the multimedia. Folks, this is where the calculations come in that you have to be able to do for testing purposes. I've made this video. It's going to be called U5A2C2 for content 2. Your formula is PS1 minus PS2, and it's absolute bars, meaning if you get a negative value, just make it positive, equals N, which is your nodal lines or destructive lines, times wavelength. So let's take a look at what this means. This is not the clearest as far as the diagram goes. That was in content 1. But what we have here is 0 nodal line. And as we go away, we've got our first nodal line or our first area with deconstructive interference, second, third. So what we want to do is take this green dot and we want to move it. Let's move it right here. So remember what your formula was. It was PS1 minus PS2. Let's figure out what PS1 and PS2 are. PS1, right here, is the distance from the opening to the green dot. PS2 is the distance from here to here. If you subtract 277 minus 289, you get an answer of 12 when we use the absolute bars, okay? So 12 is equal to n lambda when we put it in this formula up here. So lambda would be equal to PS1 minus PS2, which is 12, divided by 1, which is 12. The wavelength should be 12. Well, they tell us the answer here. They say the wavelength is 10. So I don't have this green dot in exactly the right spot. If it lined up where all of these lines crossed going down here, we would get an answer of 10 down here. So I'm just not being precise enough. This is called the first nodal line. This is the first deconstructive line out from the center. The center is 0. We cannot put this green dot anywhere on 0 and do the calculations. Let's try this again. Step 1, make sure you have this formula written down. PS1 minus PS2 equals n lambda. Let's move this green dot so it's somewhere on the second interference pattern. Okay, so there's your second interference pattern right there. There's the green dot. PS1 is 217, PS2 is 238. If you subtract those numbers, you get 21. N is equal to 2. So lambda is equal to 21 divided by 2, which is about 10. Here's one of the takeaways. Once you get these diffraction patterns, you can go anywhere on one of these nodal lines using this formula and you can get your answer. Let's go out to the third nodal line right here. So you're going to have to use your imagination to be able to see this line where the deconstructive interference is. I'm going to put that right there. PS1 is 238, PS2 is 269. That's a difference of 31. 31 is your PS1 minus PS2, n is 3, so lambda is 31 divided by 3 is 10. What this simulation is showing us is if we do double diffraction, so we take two small slits, a wave goes towards those two small slits. By analyzing the behavior of the lines, we can find out the wavelength of the light. Always remember what the bottom line is in any experiment. The bottom line here is we want the wavelength of light. This is the same technology that would be found in a spectrophotometer. You're at a crime scene, you find a piece of evidence, you heat it up to a high temperature, it gives off light, the light hits these slits, makes diffraction patterns, and the apparatus would measure the length of these lines for you. It would do PS1 minus PS2 equals n lambda, and then we have to know what our n value is. Remember, our n value is our deconstructive lines or nodes. There's 1, there's 2, there's 3. Let's take a look at 3. Where does that node line travel? Basically right back here. Okay, where's our 0? Our 0 is the middle. There's our 0 line. Let's find our 1 line. You have to use some imagination. Our 1 line goes right through here and all the way back. Now, if you do some investigation on this, there's other ways of doing these calculations. You can also use angles. We're just using one form of the calculation, and we are using this formula right here, and we are only using our dark fringes or our nodal lines. So we are only using this information right here, and all they're asking you to do here is move that green spot to different locations and see if you can find the relationship between PS1 minus PS2 in terms of lambda. Ignore this. Ignore this. As long as you can do the calculation, as long as you understand that wherever you put that green dot, as long as it's on one of these nodal lines, so if we're on 1, we should be about 10 if we're accurate. I'm at 12. If you're anywhere on 2, so this line lines up from the 2 to the base here, this number down here should be 20. 20 divided by 2 is 10. If you're on 3, your number should be about 30. 30 divided by 3 is 10. So our wavelength doesn't change, it is 10. The whole point here is wherever you put that green dot, you should always, when you put the numbers into the formula, come up with 10.